Okay, so our last unit title officially in the curriculum is called, this is fun, The Diversity of Matter and Chemical Bonding. Um, Really, it's the second two words, the last two words we need to focus on. We're going to focus on how things bond. I mentioned earlier to you guys in our kind of our year, I really consider there to be a unit on liquids because that's really our solutions unit. Unit on gases, which literally was called gases. This is kind of our unit on solids. It's not just on solids, but we're going to talk about what makes solid stuff so solid versus what makes gases and liquids not so much. Does that make sense? Now, I mean, you guys actually already kind of know some of the basic principles. We talked about three different types of motion that molecules can have. I'm talking about vibrational, rotational, and translational motion. You guys recall those terms from the previous unit? Today we're going to talk though, well, not even just today, but over the next 5 lessons, we have to talk about why certain things only have vibrational motion versus other ones that have translational motion. And really what it comes down to is bonds and interactions. What makes molecule A want to stick so close next to molecule B that it effectively forms a solid? Versus what makes molecule C and molecule D not stick together whatsoever and therefore act like a gas. Does that make sense? So that's really the focus of our last unit. You guys will probably like it in the sense that you don't need a calculator at all. There's no mathematical calculations. So this is really in contrast to stoichiometry, which was all math. This section here is pretty much all theory and understanding, which, I mean, it depends on whether you like that sort of thing versus the math. But there's basically no calculations at all. So I actually want to start off with a comic strip. This is Pearls Before Swine. Anybody ever read this one before? Pearls Before Swine is he's very clever, very witty. Here's the I'll read it out loud for you guys here. This is Rat. Rat is talking to Goat. Rat, by the way, just for some context, is a very bitter, sarcastic character. He's not very likable. So he says, "What are you reading, Goat?" And then Goat says, "Chemistry. This chapter explains how each element has valence electrons, which are what determines how easy or hard it is for one element to mix with another." Rat replies, "Sounds boring. Hey, did you get this invite to Pig's party on Friday? He wants us to RSVP. If we're not going, which I don't think I am. And I don't know. I don't think I want to go either. But I don't know what to tell him. What are you going to say?" And then the punchline, "My valence electrons do not like your valence electrons." Which is silly, but it is chemistry, so I saved it. But this really is the core of what we're going to talk about here. Why do things stick together? It comes down to one simple reason: valence electrons. That's what makes all of our matter either stay together or not stay together. Take your basic ionic bond. I'm just going to sketch things here. You guys have hopefully learned at some point. I know I've probably shown you guys this all before. What like a electron dot diagram? Let's just go with a valence level diagram. Actually, would look like for sodium. Okay, sodium has 11 protons, so those would all be in the nucleus. And then if we started putting them into rings around the outside, how many electrons go on the first energy level? Do you guys remember? Yeah, 2. So I'll put like 1 there and there. Then the next energy level has 8. So 1, 2, 3, 4, 5, 6, 7, 8. And then because sodium needs 11 electrons, we're now currently up to 10. It needs 1 more. Right? So it needs a third energy level in terms of sodium. And there's just 1 valence electron sitting out there. Right? How many valence electrons are typically the most stable formation? I don't know that I phrased that well. Yeah, 8. Normally we want 8 to be stable, and so this extra guy sitting out here, really he's got 2 choices. Either find 7 more friends, or go somewhere else. And what choice does it probably make? It goes somewhere else. It's going to lose this electron. He's going to form a cation by losing this electron. That's this electron. Now the question though is, who does it lose the electron to? If this guy is going to be a positively charged something, it needs to lose its electron to somebody who's going to become negatively charged. Yeah, that's typically how an ionic bond is going to form. Typical example of that might be, say, fluorine. We'll go with F. Fluorine is atomic number 9, so it has 9 protons. Same logic applies. In the first energy level, you need 2 electrons. In the second energy level, you need 1, 2, 3, 4, 5, 6, 7. There's an open spot for that 8th electron. If this guy can then gain an electron, he becomes an anion. So this guy will transfer electrons. And this hopefully wasn't brand new information to you guys, right? But really, that is the crux behind what we're going to talk about today, the idea that as electrons move, electrons are going to form pairs, they're going to form bonds. And as electrons form bonds, that's what keeps our matter together. If it wasn't for these slight imbalances in electrons, we would have elements, but we would not have compounds. Say that again. If it wasn't for these slight imbalances in electrons, where someone can gain or lose electrons, sure, we'd have elements. But those elements wouldn't be able to join together to form compounds. And then those compounds wouldn't be able to mix together to form mixtures. And those mixtures wouldn't be able to form together to form larger and larger forms of life. Does that make sense? So that is one way that we've seen that electrons can form a bond. The other way is how they share. Sometimes what we'll do is I'll say, actually, why don't I draw one for you? We're going to draw oxygen. You guys remember how oxygen is diatomic? It always has to come in groups of 2. The way oxygen works here is that oxygen has 8 protons, and therefore should have 8 electrons. But we're going to have 2 oxygens. And then someone might ask the question, why doesn't it come in 2s? I'm going to try to visualize this to you guys. The first energy level of oxygen, of either of these oxygens, is going to have 2 electrons. So there's 2 electrons. How many electrons does the next energy level have? 6. Yeah, 6. So I'm going to draw a new energy level right here. And what I'm going to do here, rather cleverly hopefully, is I'm going to have this guy's energy level, though, start to overlap. So rather than having them be separate, you guys can see I've kind of overlapped a little bit of a section here. And the way we're going to do this is this guy right here, I'm going to do it in color even to help illustrate it, is going to contribute 6 valence electrons. So let's say 1, 2, 3, 4, 5, 6. That guy contributed 6 valence electrons. Okay. Well, now the other guy is going to contribute his 6 valence electrons. So 1, 2, 3, 4, 5, 6. You might notice that what I've done here is collectively each of the 2 oxygens has put 2 of theirs each in this like overlapping boundary zone. Does that make sense? And what's going to happen is they're going to share. Now, I asked earlier, how many valence electrons does something need to be stable? Someone said 8, right? Well, now check this out. This guy over here, this oxygen, has 1, 2, 3, 4, 5, 6, but he's also sharing 2 of the other guy's electrons. So he now has access to 8. And then this guy over here has 1, 2, 3, 4, 5, 6 of his green ones, but then there's 2 extra right here, 7, 8. This right here, those 4 electrons, that's a bond. Okay. Really, electrons are what forms a bond. A bond is not some sort of like sticky glue, or if you ever see a picture that looks like this one here, you know, like if I show you a picture like this, some people would know that this thing right here, a little stick right there, is a bond. That's not actually what it looks like. That's what we use to visually represent it, but we now know that electrons are what make bonds. And if they share or they change electrons, that's what causes things to stick together. Does that make sense? So over the course of the unit, what I want to do is try to explain to you why this oxygen I just drew you right here, why these 2 things stick together, and yet why this oxygen and another oxygen do not stick together. Let me say that again. This individual oxygen atom and this individual oxygen atom right here, hopefully, oh my goodness, I can't even spell. Hopefully you'd agree that these 2 oxygen atoms are going to come together from a very stable bond, and that bond is what makes it O2. But what state of matter is oxygen? Gas. So then what we have to be able to also answer later is, why does this molecule right here of oxygen, why does it stay together so well, and yet if I had another oxygen over here and another oxygen over here, these guys do not attract each other? Because what would happen if all the oxygens did attract each other? What state of matter might it be? Solid or liquid? You get what I'm saying here? So I'm going to use a lot of this unit is about vocabulary. What I just described there, and we'll learn this over time, is the difference between an intermolecular bond and an intramolecular bond. One is a bond that is within the internal structure, and that's what I described right here. This is a bond within the internal structure that makes oxygen 1 and oxygen 2 bond together. And yet, once oxygen 1 and oxygen 2 bond together, other ones over here and here and here, they don't cling together. So that's ultimately our goal. So why don't I go back to this slide I had right here, because this is actually the the whole point of what I was trying to get at here. We can't see bonds. Okay? Bonds are so small that we cannot visually see them. Okay? If you want to zoom in really, really, really close with the biggest microscope you want to see, first I need you guys to know how do microscopes work. Do you guys know how a light microscope works? Okay, for those of you guys who did physics with me, you know how light is on the electromagnetic spectrum? How you go from like say X-rays, gamma rays and X-rays to visible light to radio waves and microwaves. You guys in grade 11, you guys have heard of this EMR spectrum before? Visible light is one of the portions of that spectrum. And as light goes through and passes through structures, based on the wavelength of that light, the distance between crests and peaks there, that wavelength determines the resolution as to how small you're able to see things. So light microscopes are actually pretty good. But we can actually do better than light microscopes. Does anybody know what our best microscopes are made of? Yeah, electrons, like a transmission electron microscope or a scanning electron microscope. And here's pretty much the basics of what happens. It shoots a beam of electrons, and as the beam of electrons either goes through matter or around it or bounces off of things, we're able to get a rendering of what matter looks like. Okay? Literally, you shoot a whole bunch of electrons at things, and either they phase through or they don't. And that makes sense because an electron is pretty much the smallest particle we are able to work with regularly. Right? Like we've got protons, neutrons, and electrons. Electrons are 1,000 times smaller than the other two neutrons and protons, so electrons are about as small as it gets. Here's the problem. Let's say I want to use an electron microscope to look for electrons. That's not going to work. Does that make sense? Because basically the concept is, imagine that I wanted to figure out where the hole in the wall was right there. Okay, if this analogy makes sense. And I had a whole bunch of dodgeballs. And I couldn't see anything, so I wanted to figure out where the door was. I could throw a dodgeball, and if I heard it hit the wall, then I know that's not where the gap is, right? So I throw something, boing, bounces off. Throw something, boing, bounces off. I throw something at the door, and I don't hear the boing because it bounces off. I now know that there's a gap there. Does that make sense? That's what an electron microscope does. Okay, now let's say you're trying to search for a bond. You are now looking to try to figure out what is happening right here. This does not exist. This little piece that you might see in like pretend molecules is really a bunch of electrons. So now I try to throw an electron, and I try to throw it at the wall right there, but the wall isn't a whole bunch of stuff. The wall is literally 2 electrons. It's always going to phase through. You're never going to hit anything. Does that make sense? And that is the single biggest problem we have in this unit here, is that we have no visual evidence for bonds between atoms. So this is kind of a weird section. All that we know in this section is really based on logic and like indirect experimentation. But like, it's not like we can hop on the magic school bus, shrink down to the size of an electron, and actually see a bond. Does that make sense? And that's what makes this unit very, very, to me it's actually quite cool, but it's also challenging in the way that we could be wrong on some of this stuff. There's plenty of examples in history, in science and physics and chemistry, where there was a theory about how matter worked, and the theory was great for a number of years until all of a sudden something blew it apart, and we're like, ow, that stinks. This could end up happening one day as physicists work on what protons, electrons, and neutrons are made of, and they work on quarks, and they work on string theory. These theories, they may actually have to get revised. So this is really, to the best of our knowledge, this is what we believe keeps our stuff either together or apart. So, wait, why don't I start on my notes here? I'm going to give you a bit of a history lesson. It's 1904. In terms of timeline here, this is just before Ernest Rutherford did the gold foil experiment. It's right before Niels Bohr came up with the idea of electron valence levels. Okay. And he had this thought. He figured that bonding capacity somehow has to be based on electrons. Again, this is actually pretty incredible because at the time, they didn't even know what a nucleus was yet. Let me say that again. For him to come up with this theory is pretty incredible because Rutherford had not even discovered the nucleus at this point yet. But he decided, or he realized, that there's got to be something to do with the electrons as to why a bond occurs. And, I mean, I just described this to you guys over the last little while. You're welcome. The idea that as you have excess or not quite enough electrons, this extra electron on lithium right here is what causes it to become lithium plus. Right? That one extra electron allows lithium to form bonds. And yet helium, how do we describe helium? What category does it fall under? Yeah, noble gases. And hopefully you guys know this because helium has exactly 2 electrons in its outer shell. It does not actually need more electrons, right? And so it's considered stable. And so Richard Abegg is the one that kind of came up with the idea that we now call the octet rule, which basically states that with the exception of helium and hydrogen, pretty much everything wants 8 electrons. Okay. If you can get to 8 electrons, that's a nice stable orientation. Now, in terms of bonding theory, we have to recall what I just kind of mentioned to you here is that we only believe the valence electrons are used in bonding, but like we can't hop on the magic school bus and see that. This is really just based on logical intuition and what experimental evidence says. So if I were to kind of draw a picture here of electrons, I'm just going to draw another quick picture. Here's sodium with its 11 protons. If we had 2 electrons in the first level and 8 in the next level, and then 1 in the outer level, what I'm trying to say here is that all of these electrons in here, these would be those lower level electrons. We believe that those have no implication on bonding. It's really only the outside level ones that count. So the word I need you guys to know is valence electrons. You guys know this vocabulary, right? Valence electrons, just the outsidemost level. So we believe only those ones matter. And here's another reason why. We believe that the lower electrons are actually held by the nucleus a little bit too strongly. Think about this for a second here. Why do all of these electrons not just fly away and just go wherever they want willy-nilly? There you go. Yeah, the nucleus is positive. Yeah. In terms of physics theory, there's actually a force known as the weak nuclear force, and it's believed that there's actually a force that counterbalances the electrostatic force. Because you know how your nucleus is positive? Your electrons should want to get sucked into the nucleus. They should. But there's a perfect amount of force that actually prevents those from occurring. That's that weak nuclear force. But ideally, though, those electrons want to get held by the nucleus, except for the outside ones. The further away you get in terms of distance, the less the electrostatic force applies. You guys know how, like, as you have 2 magnets, the further apart the magnets get, the less of traction there happens to be. The same thing happens with electrostatics. For those of you guys who did my physics unit with me, do you guys recall this formula? The force of attraction between things is based on charge 1, charge 2, but most importantly, it's based on the distance between them squared. For you guys who haven't seen this before, we'll do it next year. But the long story short is that if you have 2 objects that are close to each other and charged, there's a lot of force. Take those 2 exact 2 same objects, put them far apart, there's less of a force of attraction. Right? So basically the idea here is that this electron out here is way further away from that positively charged nucleus, and so it has more ability to be lost or transferred. The other thing I want to point out here is that you guys hopefully know this already. Electrons don't actually orbit. Okay? What we do instead is we call them orbitals, but really an orbital is a 3-dimension region of space where, like, somewhere in this bubble we think electrons happen to be. And somewhere in this bubble, or these 2 bubbles, we think electrons happen to be, but we don't actually even know where they happen to be. Okay, we can actually know where they were. We can't know where they are. It's a weird concept. It's Heisenberg's uncertainty principle. Here's something I need you guys to know. This might be new to you. Each orbital can either have 0, 1, or 2 electrons. What we seem to have discovered is things always seem to max out in pairs, always in a group. In this bubble right here, you can have a max of 2 electrons. You might have 1 electron, you might have 0, but we max out at 2. And here's the way this works. If you have no electrons, you have an empty orbital. If you have 2 electrons, you have a full orbital. But if you only have 1 electron, that electron is capable of either being lost or gaining another one. And we call that a bonding electron. And so really it's this number right here that makes the big difference. If you only ever have 1 electron sitting somewhere, it can do something. And I want to illustrate that to you on this slide here. Have I or Lav ever shown you guys dot diagrams like these ones right here? Are those something you've seen before? Most of you seem to be nodding here. Okay. I want to focus on the last one here then. Neon. Neon's a noble gas, right? We know that neon should not bond. And here's one of the ways that we kind of illustrate this then. Right here on the top side of the molecule, that would be considered to be where we put, like, say, an orbital. And see how there's 2 electrons right there? That's full. And then on this side right here is another kind of orbital in a way. And there's 2 electrons in it. So it is, again, full. And same thing on this side and same thing on this side. What really happens is that we believe neon has 4 orbitals, and all 4 orbitals have filled up with 2 electrons, and so it has no ability to make a bond. But if I go backwards 1 and I talk about fluorine, right here, these 2 electrons fill up an orbital, it's full, and this one does here too, and this one does here too, but here's the 4th orbital. How many electrons are in the 4th orbital? Just 1. And because there's just 1 electron in this orbital, that's what allows fluorine to accept 1 more. Does that make sense? Similar logic actually happens to the lithium right here. There's an orbital right here, 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 and here. 3 of lithium's orbitals aren't even being used. Okay, there's a spot here, here, and here, and they're not even being filled up. But here, there's the 1 extra one sitting right here. And you guys kind of already know this. If that 1 electron goes over here, it makes it a bond. And so what we can now start to do is we can start to show by representing electrons with dots how molecules fit together. And I'm just trying to remember what my next slide is here. You know what? Let's do some made-up examples right here. Like, for example, let's try to make how water fits together, H2O. Now, these dot diagrams, we call them Lewis dot diagrams. We only care about valence electrons. So what I'm going to do here is I'm just going to make up almost like a puzzle piece or like a Lego bit. I'm going to need a hydrogen. I'm going to need a second hydrogen. I'm going to need an oxygen. And what I'm going to do is I'm going to draw dots around them to represent their electrons. So how many valence electrons does hydrogen have? Yeah, just 1. How many electrons should I draw around oxygen? Good, 6 is correct. But here's the twist, though. We have to draw it correctly. So it works like this. You start drawing a single electron in each of the 4 orbitals. Okay, so that's 4. And then as soon as each of the orbitals now has 1 electron in it, now it starts to pair up. So I'm going to need to have 2 more electrons. I don't actually care which ones I pair up. So I'm going to pair up, say, this one right here. And I'll pair up that one right there. And so what we end up having now is we still have 6 electrons, but this orbital is full. This orbital is full, but this one and this one are not yet full. Does that make sense? And then honestly, think of it like Lego blocks. So my daughters are playing with Lego and they realize, hey, hang on a sec. This one right here, why don't I, let's see if I can group that together. There you go. Group. Why don't I take this one and let's do that. Hey, look, I now managed to find a way to make this orbital filled by taking the hydrogen and attaching it to that spot right there. And same logic right here. I'm going to group this together, rotate it, and there. Now all I have to do is put all of that together as one big group. And there. Now that's effectively the structure of water, HOH. Does that make sense? So this is one of the things I'm going to need to ask you guys to do during the course of this unit is there's no math to it, but it's more of like a visually conceptual kind of concept where we're trying to use logic to figure out what we think these things look like at a microscopic level. But again, keep in mind, it's very hard to look at these at the microscopic level because the bond that keeps this hydrogen and this oxygen together, that line that you sometimes see drawn where you read it as like H to O to H, that line right there is literally just 2 electrons. Does that make sense? Okay. Here's a picture that kind of shows you all those Lewis symbols. I didn't skip a slide, did I? No, I didn't. Here's a slide that shows you all those Lewis symbols, but hopefully you guys can you've seen this before or you get the picture here. Everybody in group 1 is going to have 1 dot because they all have 1 valence electron. Everybody in group 2 is going to have 2 dots because they have 2 valence electrons. The key really starts getting when you get over to here. You never group somebody together until all of the 4 orbitals have at least 1 electron inside. Okay. So you would never write beryllium like this with both dots right there. Does that make sense? Because if that was the case, then beryllium would have a full level, an empty one, an empty one, and an empty one. And by that logic, beryllium would never form a bond. Does that make sense? So never start pairing things up in groups until all four orbitals seem to have one in. Again, these are the rules that we seem to feel are true, but we can't go check. So carbon right here and silicon, you'll notice they all have 4 guys starting to be spread out. But then when you get to group 5, well, now we start pairing up. Group 6, now 2 of them have a pair. Group 7, now 3 of them have a pair. And then this last group right here, which they wrote with a 0 on top of it. I think the reason they wrote a 0 on top is because these guys right here should never have a charge. Okay. So here's the basic rules. Write the symbol, add dots for each valence electron, but do not pair electrons until all 4 sets have been filled. But I get the impression you guys have seen dot diagrams a little bit before, so I'm not going to spend too much time on it. Some of you took my physics class, and some of you will take physics. This is a slide that is not chemistry curriculum, but I love it because of the overlap. So I'm talking to you 5 because I taught you physics, and you guys will see this later. Do you guys remember the concept of entanglement? You guys remember entanglement? The idea that 2 electrons can be quantumly paired by each other, and if you separated them, this one over here, a million miles away, would impact this one over here. They're working on teleportation. You remember this concept here. This is one of the bases for why they believe this occurs. Because there's always 2 electrons in an orbital, we've discovered that if we can actually somehow measure them, I don't even know how they measure them, but they measure what's called spin. They discover that one is always spinning clockwise, and one is always spinning counterclockwise. And we actually sometimes represent those with arrows right here, saying that this electron is spinning, say, this way, and this electron is spinning that way. And if we were to separate those 2 electrons and then look at them, as soon as we see that this one is spinning counterclockwise, the one way over here must be spinning, what did I say? This one's counterclockwise, and this one's got to be clockwise. You guys recall learning about this? Very, very weird stuff. You guys, I'll show you next time we do physics. But this is actually one of the reasons why we believe that occurs, is that they always seem to come in pairs, always in groups of 2. So if you ever see a diagram like this, which I won't give you, by the way, this is beyond Chem 20, but I like how it overlaps with the other things here. You can see that you can actually have electrons that are paired in upspin and downspin. Okay, here's another diagram, but I've already talked about this one before, so I'm gonna brief this one really basically. The basic idea is that they don't actually orbit, right? Electrons are found in a region of space. Somewhere in there we find the electrons, and as soon as we look for them, they're already gone. If I haven't used this analogy with you guys before, electrons are so small that the mere presence of light actually causes them to move. If a photon of light hits an electron, it will actually move. Okay. I use this example a lot. I may as well do this again. Why do I know that you're sitting right there? How can I actually perceive that Chelsea is there? What's happening from a physics perspective? Light is bouncing off of Chelsea and towards my eyes. Does that make sense? That's why I can perceive that she is there. In the same way that a blind person could throw a rock against a wall, and if the rock hits the wall and bounces back, he knows there's a wall there. But if he throws the rock at the door and it goes through the door, then he knows that there's nothing there. Okay? Light is bouncing off of each of you and every object, and as it bounces off of you and bounces back towards my eyes, I can then perceive what's there. Now, when light happens to hit Chelsea, she still is in the same spot. Okay? But, sorry, I'm going to use you as the example still, though. Imagine that it wasn't light that hits her. What if it was, say, a cannonball? And the cannonball hits Chelsea and bounces off her and comes to me, though. Is Chelsea still going to be in the same spot, though? Well, no, it's probably going to knock her backwards a little bit, if that makes sense. That same problem occurs with light and electrons. When we look for electrons, we need some sort of light or some sort of EMR wave to hit the electrons and then bounce towards our sensors. But as soon as the light or EMR wave, like radio waves or microwaves or X-rays, hits the electron is so small that it moves. Does that make sense? And so if you can kind of envision this here, here's a particle over here. Normally what happens is light comes off of it, bounces towards me, and then I recognize, hey, this is where it was. But if light comes and hits this guy and actually causes it to bounce over here, and then I look at it, I'm going to think that the light came from right here, but the electron's now moved. Does that make sense, that analogy there? For us as people, as macroscopic objects, when light bounces off of each of you, does the light happen to hit you and knock you back? Well, no, because you're rather large. But if you were an electron You are so small that the mere presence of light touching you and bouncing off of you would actually cause you to move. So, long story short, we do not know where electrons are. We can know where they've been. We can know, like, okay, the electron used to be here when I looked for it a second ago, but as soon as I looked for it, it caused it to move. That was a big problem in Young's double slit experiment. Again, I'm looking at U5. You guys remember that double slit experiment? As soon as we looked for the electrons, they behaved as a particle, but if we didn't look for the electrons, they behaved as a wave. You guys remember that idea? You've heard of this before? So I'm going to talk more about this later when some of you do physics. Okay, but the basic concept is we do not know where electrons are. We can't. They are too small for us to narrow down. So rather than putting them in like a very defined space, we put them in like these orbital bubbles. Somewhere inside here are two electrons. We just don't know exactly where they are. We know about where they are, hence those pictures. Does that make sense? And hopefully as I teach you more physics one year, hopefully the whole picture will come together. All right, anyways, let's move on here. This is something I might actually ask you to do. Okay, I've taught you a lot of theory. Let's actually get to like a task. All I want us to do here is let's draw some Lewis symbols. Very, very basic task. How should I draw the Lewis symbol for helium? How many electrons does helium need in its valence shell? 2. Now, it's a very, very important distinction. I'm going to draw this two ways. I could draw electrons on opposite sides. I could draw 2 electrons together. Which one's the right one? Say louder. The top one? So you think it's that one there. Based on this logic here, though, this would mean that helium can form a bond and form another bond. Can helium form bonds, though? No. You get the difference here? So because of that, because we know that helium, because our experimental evidence indicates that helium does not form bonds, although there's 2 electrons, and just like beryllium or magnesium or calcium, they all have 2 electrons too. But since those guys form bonds and this one doesn't, we believe that the better way of drawing helium is actually this one right here, where in a way there's 2 electrons right here in what's known as its s orbital, and all the other orbitals are empty. Right? Because if there was 1 electron in them, it could form bonds. I want to do the one right below it then, calcium. Calcium also has 2 electrons, but rather than drawing calcium like this, it's actually better to draw calcium like this, 1 on either side. It doesn't matter whether it's top or bottom or left or right and up and down, by the way. If you drew calcium like this, I'd be fine with it. If you do calcium like this, I'd be fine with it. One of the reasons why is that when we're drawing it in 2 dimensions. But really, in real life, there's 3 dimensions. There's up, down, and in or out. Like there's X, Y, and Z dimensions. Go ahead here. I'll pause for a second here. A slit? Yeah, Young did an experiment with firing electrons through a slit. Here's the basic concept. He had what's called a double slit. So there was 2 little slips right here. And he fired electrons through it. And when the electrons went through and hit like the page on the back over here, it created what's known as an interference pattern, a phase pattern, which is a property of waves. And what it seemed to be is that what ended up happening is as the electron went through, it went through in wave fronts, and those wave fronts interfered and created a pattern like this, which made no sense at all, because you actually would expect it just to literally make 2 lines. As soon as we started detecting the electrons, they put a sensor right here. And they tried to figure out, well, did the electron go through this slit? Or did the electron go through this slit? As soon as it did that, then it actually did give 2 lines. And so the mere act of looking for the electrons seemed to actually affect their behavior. It's crazy quantum level stuff. Yeah. You've heard of some of this before, though, right? Yeah. If you guys in grade 11 would like me to tell you more about this, I'm more than willing to. But it's physics 30 I'm telling you about, so... Did I make my point well enough on this calcium right here? There's only one wrong way of drawing calcium. If you were to draw calcium like this, with both of them on the same side, that'd be incorrect. Because by that virtue, what we're trying to say then is that this orbital's full, this one's empty, this one's empty, this one's empty. And according to our logic, then calcium would never form bonds. Chlorine, let's do that one. Chlorine would need 7, so it needs like 1, 2, 3, 4. And then now I start pairing them up. So 5, 6, 7. I don't care which side has the single electron. Okay. The terminology that I'm going to use later, I may as well show you now. These guys right here are called a lone pair. Okay, I'm going to have this on future slides. If you ever have two electrons in an orbital, we call them a lone pair. A pair, because there's two of them, and lone, because they are forever and from now on alone. They are never going to interact with anybody else. These two electrons get to be by each other, and that's it. Whereas this guy right here, this guy is the key to bonds. Because this guy right here is a single one, we call him a bonding electron. In a way, this bonding electron can go out and find somebody else to join up with. And because of that, it can make compounds. So that's the terminology we're going to use over time. How would I draw sodium? Just a single dot. I don't care which side, like that. The way it works then is, of all the orbitals, sodium has one orbital with one electron in it. It has three orbitals that are completely empty, by the way. Okay, empty orbitals and orbitals with two electrons function pretty much the same way. They can't form bonds, but this is the guy that can. Oh, sorry, single one was called a bonding electron. Sorry, I didn't say that maybe very well. A pair is called a lone pair. Pair because there's two. Lone, not because there's one of them, but because now they are now alone. Okay, does that make sense? These guys right here, they are not going to bond with anybody else. But this guy right here, this single electron, that's a bonding electron. That is the whole key to all of this. As I've been saying today, the whole reason why certain things stick together and other things don't stick together is really based on these imbalances. Here's the terminology then. I didn't realize it was my very next slide. When you draw out a compound, or draw out a Lewis dot diagram, a lone pair would be like this one right here, or this one right here. These guys are lone pairs. Whereas a bonding electron would be this one right here, or this one right here. That makes sense? Okay. The next thing I need to talk about then is those electrons, they have sometimes a tendency to leave and form bonds, but other times they don't. Why? Well, I've actually already described one of them. One of them actually has to do with proximity to the nucleus. The further away you get from the nucleus, the more likely an electron is to be able to leave. Okay. Linus Pauling is the guy who kind of came up with some stuff on this. He coined the term called electronegativity. And basically the idea is that different elements, they have different abilities to either take electrons or give electrons. Okay. For example, a neon. I'll start with neon. Neon has an electronegativity of 0. And the reason why it has an electronegativity of 0 is that it doesn't want more electrons. It doesn't want to get rid of electrons. Neon is like perfectly happy exactly the way it is. So like neon doesn't even have an electronegativity. However, fluorine has the highest electronegativity. And it is capped out at the number 4.0. I don't actually need you guys to know how they make this ranking scale, by the way. But fluorine caps out at 4.0 because fluorine really, really, really wants more electrons. Okay. Do you guys have periodic tables nearby? You have a periodic table. I need to show you where to find this. I got one from me. You keep yours if I can find one. Here we go. Okay. It's actually on your periodic table. Can you guys find fluorine over here in the top right corner here? There's the number 9, which you guys hopefully know 9 is how many protons it has, atomic number. 19.00 is its molar mass. But if you go right below the 9, can you guys see what it says, that 4.0? That 4.0 is known as its electronegativity. Basically what it means is that the higher that number, the more that substance wants electrons. Does fluorine want electrons? Absolutely. Because how many electrons does fluorine have on its outside valence level? 7. Does that make sense? 2 of its electrons are in the lower shell, and there's 7 left over. Fluorine desperately wants 1 more electron. Does that make sense? So fluorine has the highest number. Now, if you go down, can you guys see how below it chlorine is 3.2? The reason why chlorine is a little bit less is that, you know when chlorine has to put its next electron in a valence shell? That valence shell is now further away from the nucleus. And so there's a little bit less likeliness of it keeping its electron because it's further away from the positive proton. And so as these molecules get bigger, you might notice that as you go down the table, the electronegativities get lower. Like next to it, number 8, oxygen's 3.4, sulfur's 2.6, eventually tellurium's 2.1, polonium's 2.0. As you go down, the reason why it gets smaller as you go down the table is that these electrons that you want to pick up have to go in further away energy levels from the nucleus, right? Here's your first energy level. Here's your second energy level. Here's your third one. Here's your fourth one. As it keeps getting bigger and bigger, the distance from the nucleus to the electron gets further away, which means the ability of the nucleus to try to attract that electron is a little bit lower. Okay. I believe I actually have that sort of thing diagrammed and shown on one of my next slides here. Yeah, here it is. Here's a picture. And it's like a three-dimensional rendering. Like fluorine right here. I don't know why it's 4.0. It's 4.1. It's usually 4.0. But fluorine has like the most affinity for electrons. Fluorine really wants electrons. But so does oxygen and nitrogen and chlorine. All of these guys right here, they'd love to have more electrons. Whereas over here, do lithium and sodium and potassium, do these guys want more electrons? Not really. If they want more electrons, they want 7 more. Right? Like sodium has just 1 valence electron. I guess you could convince sodium to pick up 7 more electrons if it had to, but it's way more likely that sodium just wants to get rid of its electron entirely. So what you end up having here is a scale then that tells you how much something wants an extra electron. The 3 criteria then, I've already shown you one, the distance from the nucleus to the valence electrons. The further away you get, the less something wants electrons. So that's why fluorine really wants electrons. But astatine, which is like 1, 2, 3, 4, 5 energy levels away, astatine doesn't really want electrons quite as much because it's so much further away now. Okay. The number of protons in the nucleus also affects things. Do that same reasoning though. The more protons you have, the more likely you are to want more electrons, because don't protons want to attract electrons? And so by that logic, when you go this way from right to left, or from left to right, can you guys see how all of these in general seem to grow? The reason why here is that tellurium has a certain number of protons, but iodine has 1 more proton. Because iodine has 1 more proton, it's more likely to want to take electrons. And then the other one I didn't talk about here is that the more inner electrons you have, they can actually shield. There's some shielding that occurs, and it prevents the nucleus from attracting the electrons. But long story short, I need you guys to be able to recognize what an electronegativity is and how it helps form bonds, because we're going to use that later on in our unit. I don't remember what else I've got here. Okay, so I want to go back to sharing versus transferring electrons here. You guys have seen pictures like this before here, right? Where we have sharing electrons versus transferring electrons. I want to focus specifically on transferring electrons right now. Let's say that I had sodium as my positive and chlorine as my negative. We can now talk about electronegativities as a way to describe this. Sodium on the periodic table has an electronegativity of 0.9. Which means that sodium really doesn't want more electrons. It's very low on the scale. Whereas chlorine has an electronegativity of 3.2. Based on that, think of it as like a fight. Who's going to win the fight for electrons? Somebody who has a 3.2 ranking or a 0.9 ranking? Well, the 3.2 ranking. And it is so good at trying to take electrons that literally chlorine is going to steal sodium's electron and say, gimme, I'm stealing and I'm a bully. However, what we're going to learn about more and more as we go into this course is that same thing actually happens in the sharing of electrons. Let's say that I were to have a bond between carbon and oxygen. Carbon and oxygen are both nonmetals. In theory, they should share their electrons. And they do. They do share, but there's kind of a spectrum here. If you guys can find the electronegativities, carbon is number 2.6. And oxygen is 3.4. Although they're going to share their electrons, they're not really going to share them very nicely. You know how I kind of showed you a picture before where there's 2 electrons kind of like in this like shared zone, if that makes sense? Well, sometimes molecules equally share them where they both have 100% access to something. But sometimes you might have a type of bond where, although they're sharing, I get it a little bit more than you. Kind of like when Kinsey and Cami are sharing toys. Let's be honest. When my 5-year-old and my 3-year-old are sharing, my 5-year-old gets the toy a little bit more than the 3-year-old. Does that make sense? But they're still sharing. You know, when I say, Kinsey, let Cammy play with that for a little while, then she gives it for 5 minutes and she takes it back again. That same thing here happens between carbon and oxygen. Who's going to take the electrons just slightly more? Yeah, oxygen, yeah. And what that ends up doing is eventually I'm going to show you this creates what's called a polar molecule. And that causes other polar molecules to stick to it. And that's what actually causes molecule A and molecule B to eventually stick together, is these slight discrepancies in electronegativities when things are supposedly sharing electrons. Sometimes oxygen takes it just a little bit more, like 51% of the time to 49% of the time. Okay. Again, I'm getting ahead of myself because I don't want to do things too far in advance, but that's what we're going to talk about eventually is these differences in electronegativities. Okay. So let me just read through my slide here. If electronegativities are both relatively high, neither atom is able to attract the bonding electron, and a sharing situation occurs, like the one I just showed you, between carbon and oxygen. Why don't I do another really common one? Why don't I do nitrogen? What's a good one here to use? Let's do S and O. You guys know this compound here, SO2? It's sulfur dioxide. Okay. If I were to ask you how things are going to work between sulfur and oxygen, you'd say, well, sulfur has a ranking of a 2.6, and oxygen has a ranking of a 3.4. Who wins this fight? Is it a knockout? No, not really. I mean, does oxygen take the electrons a little bit more than the sulfur does? Yeah, but it's that Kinsey and Cammy sharing situation. Let me do a different one here. If I did NaCl, I think I did this one earlier, didn't I? Na is 0.9, and chlorine is 3.2. Who wins this fight here? Chlorine. And it's not even close. Does that make sense? So much so that chlorine will literally steal this electron away. Okay. But here, in this scenario here, no one really wins the fight. It's kind of like a technical draw. You know, you guys know like boxing terms, how you can have like a knockout where one guy literally knocks the one guy down. But you can have a fight that goes 15 rounds. There is still a winner, so to speak, but neither of them really knocked the other one out, and so like they win on points. You guys know what I'm talking about here? Okay. That's what's happening here. No one wins. So like you have to have like a winner on points. And so what ends up happening is they share. Okay. These guys right here, the sulfur and the oxygen, there are going to be electrons in the middle that are considered to be in like the communal pool that are shared. But it really depends on who has more than the other as to how bonds get formed. And like I said, we'll learn about this more over the next few days because I can't do this all at once. Here's kind of a diagram to kind of show that concept. This is I'm going to show you water one more time now. I already drew water earlier today, but I think this one will help again. What sort of bond does water form, ionic or covalent? It actually forms covalent. And the reason why we know this is that that hydrogen is a nonmetal, and so is oxygen. Both hydrogen and oxygen are nonmetals. But we can explain this better now using electronegativity. What's the electronegativity of hydrogen? 2.2. What's the electronegativity of oxygen? Is one of them like a complete weakling where he just gives his electrons away like nothing else? Not really. I mean, I know that oxygen's clear is bigger, right? But what ends up happening in this case here is that hydrogen is still going to put up a fight. Does that make sense? This is not going to be the bully stealing the guy's lunch money. And so when these guys fight for their electrons, they don't actually have a winner-take-all situation. You guys can see in this picture right here, what ends up happening is right here, these electrons are in the communal pool. They're being shared. Does that make sense? What I'm going to show you, this is probably where I'm going to end, because I think I'm almost done, right? Yeah, we're getting close to the end here. What we're going to start doing tomorrow is I'm going to show you why water is a liquid. And I'll do that today, just with like a little bit of like a spoiler here. Water is a liquid. Okay. Here's one of the reasons why, is that when water forms a bond, it kind of looks like this. You have hydrogen bonding to oxygen, bonding to hydrogen again. And you guys can see that there's a lone pair of electrons sitting out here. Based on the way this works, we actually have to account for those lone pairs right here. And so it kind of makes this shape here. Hydrogen has 2 electrons shared right here bonding to oxygen. This hydrogen has 2 electrons right here, bonding to oxygen. But these guys right here and these guys right here were not part of a bond. But I'm still going to account for them right here and right here. Okay. Now what ends up happening, though, is when we consider how the fight occurs, oxygen wins the fight. So oxygen was a, what was it, 3.4? Oxygen is a 3.4. Hydrogen is a 2.2. What ends up happening is these electrons right here, rather than being right in the middle of the bond here, really they're closer to oxygen's side. And the same thing right here. And sometimes you have the electrons over there instead, but they're not shared equally. Because of that, what ends up occurring is that oxygen takes more of the negatives and hydrogen takes slightly more of the positives. And what it creates is a bit of an imbalance where this molecule right here ends up having positive ends over here, just slightly positive. And this oxygen over here has negative ends right here. And that's what causes this water molecule and another water molecule to eventually stick together. Because the oxygen side of the molecule is negatively charged just a little bit. Because it wins the fight ever so slightly. And the hydrogen end of the molecule is positively charged, but just slightly positive. Because it doesn't quite lose, it loses on points. Okay? And what that causes is this oxygen right here and this other hydrogen and other molecule, they can stick together. And that helps explain why water is a liquid. Because there's a reason for this molecule and this molecule to attract to each other. Right? If I were to draw another water molecule over here, another H to an O to an H, again, this oxygen right here wins the fight ever so slightly, so we call them negative. These hydrogens become positive, and then this hydrogen and that negative there, they attract. Okay? So over time, as we build up and learn more about this, what we're going to talk about is this bond right here is called an intramolecular bond. Molecular bond. Where this is a bond inside a molecule. But based on there not being a clear winner to this fight, it causes a slight lopsided discrepancy, which means that right here, we can actually have what's called an intermolecular bond, which is between this molecule here as a collective and this molecule here as a collective. And because of this intermolecular bond, water wants to stick together, and because of that, water is in a liquid form. Not only that, water is actually really easy to turn into a solid form because really water turns into a solid as soon as it gets below 0, which doesn't really take a whole lot for us. Now, if that makes any sort of sense, that's fantastic because I basically taught you the whole unit. Okay, but like I'm going to do a more thorough job of it, lesson by lesson. I want to still build up, but that's basically the concept. Is we can now try to describe why water is a liquid, and did I lose you guys really badly here? Can I show you one more example then? I'm going to show you carbon dioxide as a counterbalance. You know how water is H2O? Water is usually in a liquid format. I want to show you CO2, which is in a gas format. I want to explain why do two molecules, which for all intents and purposes like have the exact same structural formula, why is one a liquid and one's a gas? So again, it's all about electronegativity. If I were to piece this one together, carbon looks like this, 1, 2, 3, 4 valence electrons. And oxygen, the two oxygens you need, look like this. That one there, and this one here. Over time, what I'm going to hopefully show you how to do is how to take these pieces and merge them together. Okay. Imagine they're Lego blocks. If I were to take this one right here and try to piece it together, why don't I take this guy here? Oh, goodness, I want the whole thing to go. Well, imagine I could lift it up. Let's say I took this one right here and I kind of superimposed it like there. See how I'm kind of making a bond sitting right there? And if I were to take the other one right here, I'll kind of put it there. Oxygen, I'll do some lone pairs. Put it right there. What actually ends up happening is you end up having some shared electrons in this pool and this pool right here. But that's not enough because there's still an extra electron kind of kicking around everywhere over here. So what ends up happening is these ones here are also in the shared pool. Like this one and this one come and join in over here. And this one come and join in right there. It actually creates what's called a double bond. I'll show you more about this again tomorrow. But it creates a molecule that looks like this. Now what happens in this particular molecule, though, is you also have a fight for electrons. Carbon is a 2.6, and an oxygen is a 3.4. Is there a winner? Yes. Not by clear knockout, but there is a winner. What ends up happening is the oxygen end over here becomes slightly negative, and this oxygen over here becomes slightly negative, and the carbon in the middle becomes slightly positive. But here's the big difference. Because of the way this molecule is shaped, and again, I'll show you this as we go along, what ends up happening is this one pulls directly out, and this one pulls directly out. Because of its symmetry, this guy's actually neutral. Water had a little bit of a bend to it, and because of these lone pairs sitting down here, water had a little bit of a bend to it. And so when that occurred right here, it caused water to be slightly lopsided, just slightly, but enough that this water molecule can stick to this water molecule right here. Carbon dioxide does not have a bend shape to it because it's completely flat. The word we're going to use is linear. What ends up happening is this carbon dioxide and another carbon dioxide actually have no reason to stick to each other due to the way their polarities work. Okay? And that's what I'm going to try to show you guys over the course of our unit. But, I mean, I basically showed you everything all of a sudden, so if you feel overwhelmed, please don't freak out, okay? Okay, why don't I finish off my last slides here, and then we'll call it a day. So here's the main concept that I was trying to show you by going way further than I need to. It's all about electronegativities. You guys have actually previously learned from me that we form bonds based on either being ionic or covalent, but that's actually really not true. That was a simplification. When bonds are formed, you have to think of it as a fight for electrons. If an ionic bond forms, what really happened is there was a knockout. Somebody literally stole the other guy's electrons. Oh. It was like a TKO. Somebody knocks them down to the ground. But if you have a covalent bond, there was a sharing of electrons. Now, when they share, it may not be equal sharing, but like nobody really officially wins. And so you can't really think of ionic and covalent bonds as actually being about between metals and nonmetals. That's actually a really grade 10 definition. It works, but what we're going to do is we're going to change our definition from now on. It really has to do with who wins the electronegativity fight. Okay. Ionic bonds, though, here's one of the problems, though. Ionic bonds are not very strong. How do you break an ionic bond? Think back to our first unit. What happens when you take an ionic substance and put it in water? It dissociates. You can actually break ionic bonds quite easily. All you need is water to do so. So although ionic things are often solid, it's actually very easy to turn them into an aqueous state because of the fact that it can dissociate in water. Okay? But in general, if ionic bonds are going to cause a complete separation, what that ends up causing is this sodium becomes positive, and this chlorine becomes negative, and another chlorine over here becomes negative, and another one becomes positive. And these guys right here, they're going to want to attract to each other. And that creates a very, very stable, until you break it up with water, but a very stable formation, which creates a solid. And that's what happens in ionic compounds. There's actually one more type of bonding that we don't actually teach you about in grade 10. It's called metallic bonding. And it's a kind of bonding that occurs just between metals. Okay. You know how you can have a metal and a nonmetal? That's an ionic bond. You can have two nonmetals. That's a covalent bond. That was like our old definitions. I kind of didn't tell you about the third type. You can actually have two metals. Okay. We call that metallic bonding. We actually see that sometimes when you make an alloy. Do you guys know what alloys are? It's where you like melt two different metals together, like say iron and carbon together. I think iron and carbon, I believe, is steel, if I have that one right. Well, what ends up happening in those ones there is that nobody wants the electrons. Okay? Look at the electronegativities for, say, zinc and for copper. Can you guys find zinc and copper, 29 and 30 on the table? One is 1.7 and one is 1.9. Do either of those guys really want electrons? Do either of them have like a high number where they're great in their ranking? No, so what ends up happening in metallic bonding is nobody wants the electrons. Well, and if nobody wants the electrons, guess what that's useful for? These things can conduct. Yeah, that's what's wonderful about them, is that if nobody wants the electrons, then the electrons can just go wherever the heck they want. And if they go in a circuit, like I'm teaching my grade 9s right now, if you have a closed loop, you can have electricity. Does that make sense? And so that's kind of this picture I found right here, is that all of these positive nuclei, they have electrons. But if none of the nuclei really want the electrons, then the electrons are kind of like, I don't know, they're like emancipated minors who can just go wherever they want. They're no longer tied to their parents. They stay out till all hours of the night. They're up until 2 a.m. and they decide, well, I'm not going to stay here. I'm going to go over here and over there and then back around again. Does that make sense? And so that's metallic bonding, where you have two metals stacked together. So what we end up then is a spectrum. I want to finish with this slide. I'm going to call it a day here. I have a spectrum here of bonding. And it's all about electronegativity differences. Okay. Let's say that you have a huge difference. Like, say, a 4.0 trying to fight a 0.9. What happens in that case? What do we call that? Yeah, we traditionally have called it an ionic bond. And the reason why we call it an ionic bond is that those things always occur between positives and negatives, metals and nonmetals. But now a better definition of this is that a huge difference in electronegativity really means that you have a winner. And so therefore you have electron transfer. Does that make sense? On the other end of the spectrum, you don't have a winner. And this can take place in two different ways. They can either both be high electronegativities, or they can both be low electronegativities. Now, if they're both high electronegativities, like say a 2.6 versus a 3.4, what happens in this case here? What did we traditionally call this? Covalent. Where what ends up happening over here is that they have to share the electrons. Now, it might not be equal sharing, and that unequal sharing is actually the real key to all of this, as we learn in our next few lessons. But as the electronegativity difference is not a complete knockout, they have to share their electrons in that communal pool. We call that covalent bonding. Okay, at least that's what we call it, like when we're learning in grade 10. We still use those terms, but like our definitions change. The reason why now is based on fighting for electrons. Okay. But there's another possibility. What if they both have low electronegativities, like say a 1.2 and a 1.3? What ends up happening here? Nobody wants electrons. This is metallic bonding. Not that they share the electrons. It's that the electrons are free to go wherever the heck they want. So like I said, these are the electrons that are staying out until 4 in the morning, and they're not staying home at all. You know what I'm saying here? And they're free to travel wherever they want. But the cool thing about these ones here is that they conduct. Okay. That's actually about as far as we go into metallic bonding, though, because really there's not that much interesting about them otherwise. All you do is you take two metals, you melt them together, or three metals, you melt them together, and you create a metallic bond where you basically have an alloy, a mixture of metals. Okay. We're going to focus a lot on these two over the next couple of days, though, as I teach more. Okay. And hopefully, as I do this, more and more I'm going to be able to explain to you why certain things stick together and why certain things don't stick together. So, that's all I got for today. Questions? Did I make sense so far? Okay. I want to build way better on this, but I kind of have taught you guys kind of the real basics of the unit. I went way beyond this set of notes. Tomorrow, let's talk about explaining molecular formulas. And what we're going to do is we're going to start trying to draw more and more molecules. The other thing I'm going to do, if I can find them for you guys here, I have molecular model kits back here. Here they are. Have you guys seen these before at some point? These are fun. I'm going to give you some of these, and you guys get to kind of play around, where you're actually going to make molecules using these like ball and stick figure things. You guys ever seen these? It's kind of fun. Now, one of the things I do got to point out, though, maybe one of the biggest things from this unit here, is this what this actually looks like? No. We use this because I think this is easier for our brains to interpret, but like this thing right here, what is this actually? Electrons, yeah. Now, usually it's 2 electrons. It can be 4 or 6, actually. There's different numbers you can have. But this thing right here is not actually a stick. It's electrons. And this thing right here, what is this trying to represent? The nucleus of the element plus all of its other electrons, except for the electron that forms the bond. Does that make sense? And this bond can take place in a lot of different ways. This could be a sharing of electrons. This could be a transferring of electrons. This could be even sharing. This could be uneven sharing. And depending on how that works, plus depending on the shape of the molecule, here's one shape we're going to see. Let me show you another one real quick here. To find the right one in here. Come on. Where is it? There we go. Whereas if I showed you this shape right here, see how there's a little bit of a difference in shape here? This one is straight across. This was carbon dioxide, by the way. It was flat across. Whereas this one right here is what water looks like. One of them is completely flat across. One of them has a little bit of a bend to it. And as I show you why, this will help explain why this carbon monoxide, this carbon dioxide, and other ones don't stick together, but why this water molecule does stick to other waters. Which is why this is a gas, this is a liquid. So. Anyways, why don't I call it a day there? We'll keep this going tomorrow. If you guys would like, feel free to start looking at your assignment, but I'm not even sure you're going to want to do a lot of questions until I teach you more, because what I don't want you guys to do is to answer a question, and then I kind of give you like a better explanation of it as we go along, and then you have to like go back and change your answers, if that makes sense. So if you don't start your assignment, by the way, for at least another couple days, that's fine by me. So, sound good? Okay, I guess we're done.